We can start the last part of the afternoon session. And the first talk is by Yoden from Kyoto Daigatsu, Kyoto University, speaking on jet formation in decaying two-dimensional turbulence on a rotating sphere. And you have 28 minutes before you ask for questions.
Thank you. So this is my title and the course and we talk about the two-dimensional turbulence on the rotating sphere, and the starting point is the forced turbulence done by Gareth Williams in 1978. At that time, the computer resource is limited, so he assumed a zonal periodic condition and symmetricity with the equator. And about 15 years ago, myself and Yamada did a similar experiment for the decaying turbulence in the full spherical geometry for non-divergent fluid. And we found this kind of zonal band structures and this strong retrograde or westward circumpolar jet. And Cho and Polvani in 1996 did a similar decaying turbulence in the shallow water system, and they found this retrograde equatorial jet. And since then, we have done lots of computations, and the early one is some analysis of this. Our title is decaying turbulence, but the forcing scale is greater than the line scale. So our current interpretation is that this is totally a Rossby wave dynamics to form this circumpolar jet. And also we did forced distributed turbulence computations. And nearly 3 years ago, Walter Robinson and myself organized the AGU Chapman conference on the title of Jets and Annular Structures in Geophysical Fluids. And one of the motivations is this kind of jet formation in the turbulence in the rotating sphere. And most of this result is discussed at that meeting, and some progress of the interpretation or understanding the dynamics. So in this talk, I summarize our two experiments on shallow water, decaying turbulence, including the non-divergent fluid with zero fluid number. And first one, Hayashi et al. Discussed did a parameter sweep experiment in wide ranges to examine the dependence of the structure of zonal jet and to understand the importance of Rossby wave dynamics. And the second paper published by Kitamura and Ishioka, they did a large number of ensemble experiments to answer the following questions. How robust is the emergence of the equatorial retrograde jet? What's the formation mechanism of the equatorial jet? And thirdly, can we obtain the prograde, eastward equatorial jet? The first paper, Hayashi et al. Investigated Rossby waves and jets in a two-dimensional decaying turbulence or rotating sphere. Here is the model equations. This is a non-dimensional shallow water equation on a rotating sphere, and it's basically the standard notations. And there's two non-dimensional parameters. Omega is the rotation rate of the sphere, normalized this, and the fluid number defined as this. And here is the experimental parameters. First series, we fix the fluid number and change the rotation rate from this range. And the second series, we fix the rotation in some high rotation rates and change the fluid number to 0 in the barotropic fluid case. And this shows the k beta, and this is the Rhine's wave number. And these two numbers is radius of deformation at the pole, and this is a radius of deformation at the equator under the assumption of equatorial beta plane. And we also introduced this deformation radius for each latitude divided by this local Coriolis parameter. And here we introduce a key latitude denoted by phi at where this local deformation ratio equal to the lines scale. So this is the experiment setup. We use a spectral discretization with truncation total wave number 170 in the spherical harmonics. And we use the classical fourth-order Runge-Kutta method. And the initial condition is a random velocity field like this. And the energy peak exists at the total wave number n equal 50. And its wave number is much larger than the line's wave number. And we use the same initial condition for all the experiment. And note that even in the shallow water system, there's no height variation, only we force initial vorticity field. So in some cases, there is a strong initial adjustment process due to the change of the elevation. So this is a result for the vorticity field, relative vorticity field at peak of 5. For 5 fluid number, and I think if we think about the Jovian atmosphere, this rotation rate is roughly the same with this experimental condition, and the fluid number is, I think, between this and this. And for the Earth's atmosphere, rotation rate is much smaller, maybe 40 or 50, and the fluid number, again, between these parameter settings. So these green lines show the key latitude phi at where the local deformation radius equal to the line scale. And this gives a good estimate of latitudinal extent of zonally elongated structures between these latitudes. So it's confined nearly the equatorial region and getting larger due to the decrease of fluid number. Okay. And beyond that latitude, coherent vortices appear. And there are some hint of this kind of inclination near this latitude, indicative of some approaching the Rossby wave to this critical latitude.
Show us PV for those cases.
No slide we have.
Well, I
but
conjecture the PV contour is still coherent around
yeah,
latitude,
but I think here's omega is very large, so it's nearly the there's the undulation, but
I mean, you're intercepting the cascade before they bunch up, before they come on close enough.
so it looks like vortices up in the high latitudes at the top left, but actually there are going to be PV contours wandering in between the vortices.
I think I can show some animations for later on the total PV field. So yeah, at that time. In the second part of this talk. And this is time evolution from t equal 0.1 to 10 in log scale in the x-axis of zonal mean angular momentum for 5 value of the fluid number. And again, the same parameter. And there's a 2-stage. There is a first establishment of a banded structure of zonal mean zonal flows with alternating directions between these key mainly between these key latitudes. So you can see this. And the other is a slow continuous growth to increase this westward jet in equatorial region or polar region in the barotropic case. So this is a time evolution for the same plot in log scale in that time to show the cumulative eddy angular momentum flux for the same parameters. And in slow continual growth to intensify intense westward jet, and there is a systematic momentum flux from wider latitudinal extent compared to the width of the equatorial jet or circumpolar jet. So this is indicative of the long distance influence of Rossby waves to accelerate this kind of jets. So this is a summary of the first part. This is a summary of the parameter dependence. And when the flow is non-divergent and omega large, a banded structure, mean zonal flow, with alternating flow directions appears. And intense westward circumpolar jet tend to emerge in both poles or either, depending on the initial condition. When the system allows the surface elevation, or we think about the shallow water system, this circumpolar vortex, circumpolar jet disappear, and an equatorial westward jet emerges with increasing the fluid number.
Are you planning to talk about why they form, where they form?
For the equatorial, the second part we discuss using the weekly nonlinear analysis. And the time evolution has the 2 phases. First is the appearance of a banded structure of zonal mean zonal flows with alternate flow directions in the first time scale, and mainly due to the local PV mixing, but it's not a complete staircase because this is a decaying turbulence. And meridional extent of the banded structure roughly corresponds to this key latitude where local deformation radius is equal to the line scale. And this is pointed out by Tice. And in the shallow and fluid number is not so small. This area limited to the equatorial region, and if we limit the fluid number to 0, it spread whole the spherical domain due to this relationship. And in the slower time scale, there is an intensification of westward jet when omega is large. And weakly nonlinear dynamics explain this angular momentum transport associated with Rossby wave, and not local PV mixing.
Oh, so these Rossby waves don't break at all? PV contours simply undulate?
Break. Yeah, we can see some.
You say there's no PV mixing at all?
No, relatively, the effect is relatively small.
Okay.
Not full mixing. And if fluid number equals small or 0, jet appear near the pole where beta equals 0. And if not small, the jet appears at the equator. So now one of the interest points of the direction of the equatorial jet. In this particular example, we obtained one example of eastward jet, prograde jet on the equator for the small rotation, slower rotation case. So I want to introduce the second paper by Kitamura and Ishioka. And Kitamura is here, so you may ask all the questions to him. And the title is Equatorial Jet in Decaying Shallow Water Turbulence on a Rotating Sphere. So experimental setup is nearly identical to the previous one, but in this case, they did an ensemble experiment by changing the initial conditions up to the 1,000 members for the particular combination of the external parameters. And they did these 3 cases. And they changed the definition a little. So this combination parameter corresponds this value for the previous Hayashi et al. Paper. So this is an example of the time of evolution of potential vortex field for the case of the retrograde jet. So it's a westward jet. So I think this animation repeat.
What are the white spots? What are the white spots?
It's a low potential vorticity. So Antarctica is a minimum and maximum due to the rotation of the planet.
Where's the critical latitude for this one?
I don't remember exactly how many years.
Near the equator.
Yeah, I'll check after. And so you'll see the undulation of the PV contours and some signature of the overturning. Okay, this is so you'll see the and the other is a prograde jet. So this is the same fluid and Rossby number, but you'll see the formation of eastward jet.
You ever see Kelvin
Not so much. Most of the Rossby gravity and Rossby waves to determine this kind of acceleration. I can show the analysis soon. So you'll see this kind of spotty coherent velocity in the high latitude with opposite sign. So vortex too strong. Yeah, mergers and such kind of thing. So in this case, there is some strong gradient around the equatorial. So here is some schematic this illustration for the meridional distribution of zonal mean zonal flow for prograde jet and retrograde jet and PB. So there is some well mixed region in both sides of this prograde jet, and this is the second example, and this is the first is well mixed along the equatorial belt. And they did the ensemble experiment for 3 parameters, and this is a histogram of zonal mean zonal flow at the equator for time 5 and time 15. So in the early stage, you will see the nearly 50-50, roughly 50-50 chance of the prograde and retrograde jet. But afterwards, in the case of a small Rossby number, this disappears. There remains only the westward jet. But very interestingly, even in this case of the T15, some amount remains with a positive eastward jet, prograde jet. And they did 1,000 ensemble trials to confirm the robustness of this component. And they also did evaluation of the second order acceleration of mean zonal jet due to linear waves. So they use the linearized equations with a time constant zonally symmetric basic flows with these 2 types, and integrated from the eddy field obtained the full nonlinear model at the time t equals 5. And the first one is a no flow case, and the second one is a weak idealized prograde mean flow. And they did up to 125 member of ensemble runs, and in the time integrations, second order acceleration mean zonal flow by the linear disturbance is evaluated. And this accumulation is separated into each component of a normal mode, normal mode of waves with this flow field. It's a half mode, and divided into 4 classes: Rossby waves, gravity waves, Rossby gravity waves, and Kelvin waves. And this is the first example of the accumulation of zonal mean angular momentum between t equals 5 and t 15 for the basic flow without zonal flow. Okay. And this is a 50 prograde members. So nonlinear runs, they obtained the prograde jet. And they took the wave eddy field. But this accumulation is negative. So this cannot explain this formation of prograde jet. And the dominant one is the Rossby component, others is nearly 0. And this is a case for the 50 retrograde members. And large part of this acceleration can be explained this linear computations. And this can be explained this Rossby wave dispersion relationship. At the equator, this deformation radius has a maximum, so this is minimum. So this is a positive constant minus. So this is largest as the equator. That means effective dissipation of this component along the equator. That's the main reason to produce this negative acceleration at the equator. So to explain the acceleration of mean angular momentum at the equator with positive sign, they took another experiment with a weak prograde jet and computed the dispersion of with the same 50 ensemble members. And they obtained this nice positive accumulation along the equator, and nearly half of this is explained by the only one single westward moving Rossby gravity waves. And this is a illustration of jet intensification mechanism by Rossby gravity waves. So this is Rossby gravity waves without shear, but in this case they assume a weak prograde jet. So they deform this mode like this, and that introduces a horizontal momentum flux that intensifies this period. So this is a summary. A prograde equator jet can exist for some combination of Rossby and Flume numbers, while there is no prograde jet for smaller Rossby number. And there are two types of mechanisms exist for the second order acceleration of the equatorial jet by waves. First one is increase the local meridional member or Rossby waves. And the second is a tilting mechanism, tilting of equatorial waves due to the meridional shear of the mean zonal flow. And each acceleration mechanism works as follows. Mechanism 1 is dominant when the Rossby deformation radius is small and works as a retrograde acceleration in the equatorial region. And the second mechanism works as a positive feedback for intermediate deformation radius case, but it cannot work without that prescribed equatorial prograde jet. And here's some concluding remarks. And I think I want to point out this kind of dependence of Rossby deformation is recently reported as three-dimensional beta plane decaying turbulence computations. And equatorial zonal jet formation can be understood by the acceleration mainly due to the weakly nonlinear Rossby beta. And I want to show some thing in the recent papers. So this morning, Richard Scott showed this nice work. And I still have a question on this result of the, he showed this insensitivity of the formation of nice eastward jet, independent of the choice of the deformation radius. It's still puzzling between the forced and our decaying case. And the second one is a very different new model for the equatorial jet. Farrell and Ulanov recently submitted this paper using their SSST theory for an equatorial beta plane. And this is a parameter of the intensity of the turbulent velocity, and they showed some two equilibrium state for some parameter ranges. But this westward jet disappear for the larger forcing. So this is a time evolution from here to show the transitions. For large enough forcing case, there only the eastward jet. So this is a weak, so there is a two jet, and the equator is westward. But if change this, there is a transition to this state. The system is very different, some idealized situation, but yeah, there's some interest work on this equatorial jet and its dynamics. And thank you very much for your attention.
Questions?
Do you resolve strongly ageostrophic waves like Kelvin waves or eastward propagating Yanai waves?
The linear computation shows the contribution of such kind of components very small.
But this because your Rossby numbers are very
So-
small. And these waves are
So
ageostrophic.
initial conditions, there are some component.
Because in principle, the eastward propagating Yanai wave will work in the opposite direction. But this will probably happen when Rossby numbers will be much greater, right?
Kelvin, Yana,
No, I mean Yanai, mixed Rossby gravity.
mix, yeah. Yanai wave is, we call the Rossby gravity.
Yeah, but you are considering only westward propagating Yanai wave, right? But there are eastward propagating Yanai waves too. Yes,
first frequency.
Yeah.
But I think, we categorize that to the gravity waves.
Maybe you can discuss this afterwards. Is there any other questions?
I can't quickly do the inventory for our solar system as to how many prograde and retrograde jets we have, but it's starting to look like a matter of chance.
Yeah, I remember we first published that 93. Spiegel commented that distribution of the circumpolar eastward jet looks like the solar system. I don't know further.
About half each way. 50-50.
50.
Like flipping a coin.
Okay. I think we need to get on to the next topic.